There is a place at the very boundary of everything we call home. A place so remote that even the sun, the massive burning heart of our solar system, looks no different from any other pinprick of light scattered across the black. Most people have forgotten about it. After all, it was stripped of its title, demoted, dismissed, declared too small to matter. But here's what those people don't know. What waits at the edge of the solar system is not a dead, forgotten rock. It is something that should not be possible. A world that defies almost every rule scientists thought they understood about how planets form, how they age, and what cold and darkness do to a world over billions of years. This is not a story about a rock in space. This is the story about how everything we thought we knew turned out to be wrong. This is the real story of Pluto. In 1930, a 24-year-old farm boy from Kansas was scanning photographic plates at the Lowell Observatory in Arizona. His name was Clyde Tombaugh. He had no advanced degree, no formal training in astronomy. He had taught himself the night sky by staring at it from a field in the American Midwest. And on February 18th, flipping between two photographs taken days apart, he noticed something. A tiny point of light had moved. It shifted position the way planets shift position against the fixed background of stars. He stared at it for 45 minutes before he told anyone. Then he walked down the hall and said quietly that he believed he had found a new planet. He had. Pluto was announced to the world on March 13, 1930. The date was chosen deliberately. It was the birthday of Percival Lowell, the wealthy astronomer who had funded the search and spent years predicting that a ninth planet must exist. He had died 14 years earlier, never knowing whether he was right. The name Pluto was suggested by an 11-year-old girl in Oxford, England. Venetia Burney had been eating breakfast with her grandfather when he read her the news from the morning paper. She thought the name fit. God of the underworld. God of the deep, cold dark. She was right. But even she could not have imagined just how much that name would come to mean, how accurate a description it would turn out to be. For the next 75 years, Pluto sat at the edge of the solar system and told us almost nothing. From Earth, even the most powerful telescopes could only resolve it as a smeared blob of light. We knew it was small. We suspected it was cold. We assumed it was dead. We were about to find out how completely wrong we were.
In January 2006, a spacecraft the size of a grand piano was launched from Cape Canaveral on top of a rocket moving faster than almost any object humans have ever built. It was called New Horizons. To reach Pluto in any reasonable time frame, engineers had calculated something remarkable. The spacecraft would need to swing past Jupiter, use the giant planet's gravity like a slingshot, and be hurled outward at nearly 84,000 kilometers per hour. Even at that speed, the journey would take 9.5 years. 9.5 years of traveling through the void between worlds. 9.5 years before it would finally arrive at its destination. For much of that time, the spacecraft was put into hibernation, its instruments powered down, its systems resting. A tiny machine drifting through the darkness like something waiting to be woken up. The team that built it watched it go, then waited some more. Some of them spent nearly a decade of their lives thinking about a world they had never seen clearly, wondering what they would find when they finally arrived. The fear was simple. Space is not empty. The outer solar system is filled with debris, dust, ice fragments, microscopic particles traveling at enormous speeds. A single grain of sand moving fast enough can punch through metal. To reach Pluto, New Horizons would have to thread a needle through unknown territory. And unlike a robot on Mars, there was no way to stop, reverse course, or wait for the danger to pass. The spacecraft would fly through the Pluto system in less than a single day. One shot, one chance. After nearly a decade of travel. On July 14, 2015, New Horizons reached its closest approach. It passed within 12,500 kilometers of Pluto's surface. And what it sent back would change the way scientists think about the outer solar system forever. The first clear images arrived slowly, one pixel at a time, assembling themselves like a painting emerging from static. And then, there it was. A feature so strange and so prominent that it immediately dominated every conversation about what New Horizons was finding. A massive, bright region, shaped unmistakably like a heart, sitting near the equator of Pluto. It stretched roughly 2,500 kilometers across, the distance from New York to Los Angeles. Scientists named it Tombaugh Regio, after the man who had first noticed that moving point of light 65 years earlier. But what it contained was anything but sentimental. The left lobe of the heart is a vast basin. It sits approximately 3 kilometers lower than most of the surrounding terrain, and it is filled to the brim with one of the most geologically active surfaces anywhere in the outer solar system. This region, called Sputnik Planitia, is covered in nitrogen ice, not frozen water, nitrogen. The gas that you're breathing right now, the gas that makes up 78% of Earth's atmosphere, is so cold on Pluto that it has solidified into a thick, flowing glacier. And it is flowing right now, slowly, imperceptibly, but moving. The nitrogen ice in Sputnik Planitia is not sitting still. It is circulating. Driven by heat rising from below and cold descending from above, the ice turns over in enormous convection cells, each one hundreds of kilometers wide. Like the surface of a pot of extremely thick, extremely slow, extremely cold liquid, Pluto's heart is churning, constantly erasing the marks left by ancient impacts, constantly resurfacing itself, renewing what should have been frozen solid billions of years ago. Scientists stared at this region and felt the ground shift under their understanding of what planets can do, because Sputnik Planitia has no impact craters, not one. On a world that has existed for 4.5 billion years, in a region of space where asteroid impacts have been raining down since the solar system formed, the surface looks brand new. Something is erasing the past. Something is keeping Pluto alive.
Look to the edges of Sputnik Planitia. Where the nitrogen glacier ends, something else begins. Mountains. Not gentle hills, not low ridges. Mountains of genuine scale, rising 3, 4, sometimes 5 kilometers above the surrounding terrain. As tall as the Rockies, as dramatic as the Alps. But they are not made of rock. On Pluto, there is no rock at the surface in any traditional sense. The temperatures are so extreme, the environment so hostile to the chemistry of stone, that the mountains of Pluto are made of something else entirely. They are made of water ice. Water ice so cold that it has become structurally rigid, hard as granite, immovable as bedrock. On Earth, ice melts. It flows. It is temporary. On Pluto, water ice is a permanent geological material, the foundation of every mountain range, the bedrock of an entire world. This feels like it should be obvious in hindsight. Of course, water ice would behave like rock if it were cold enough. Of course, a world in deep space would find different ways to build its landscapes. But standing in front of the image for the first time, seeing mountains that could exist in any mountain range on Earth, and knowing they were made entirely of frozen water, felt profoundly strange to the scientists who first saw it. One of those mountain ranges was quickly nicknamed the Hillary Montes and the Tenzing Montes, after the first climbers to summit Everest, because Pluto, this tiny, demoted, supposedly insignificant world, had peaks worthy of being named after the greatest mountaineers in human history. There are also stranger formations,
towers and spires of methane ice, hundreds of meters tall, arranged in fields across parts of Pluto's landscape. Scientists call them bladed terrain. They look almost like the fins on some enormous machine or the scales on a creature too large to comprehend. They likely formed over millions of years as methane ice slowly sublimated and refroze, building upward layer by layer, in a process that has no real equivalent anywhere else in the solar system. Pluto builds things. In temperatures colder than liquid nitrogen, in darkness so deep that noon looks like a moonlit night on Earth, Pluto builds mountains and towers and plains that spread across hundreds of kilometers. How? The answer to that question pulls at something even deeper, something hidden beneath the surface, something that should not be there. Consider what Pluto is, a small world, roughly 2/3 the diameter of Earth's moon, located nearly 6 billion kilometers from the Sun. At that distance, the Sun delivers roughly 1,600 times less heat to each square meter of surface than it does on Earth. The temperature averages around 44 degrees above absolute zero. That is not just cold. That is the kind of cold that strips the meaning from the word. That is the cold of deep space itself, barely modified by proximity to a star that looks no bigger or brighter than Venus does from Earth on a clear night. At that temperature, there should be no movement. There should be no activity. There should be nothing left to surprise us. And yet, the shape of Sputnik Planitia tells a story that scientists did not expect. The basin sits almost perfectly aligned with Pluto's largest moon, Charon. The two are tidally locked. Pluto always shows the same face to Charon. Charon always shows the same face to Pluto. They orbit each other like two dancers who have never looked away. And Sputnik Planitia sits almost exactly on the line that connects the two. This is not a coincidence. For a feature that massive to align itself with the tidal axis of the Pluto-Charon system, something beneath the surface must have pulled it there. The most likely explanation? A liquid ocean. Buried beneath roughly 150 to 200 kilometers of ice, shielded from the cold of space by an insulating crust, warmed from below by the slow decay of radioactive elements inside Pluto's rocky core, a liquid ocean of water may have existed on Pluto for billions of years. The mass of that liquid ocean would be enough to pull Sputnik Planitia into alignment with Charon, like a heavy ball bearing settling into the lowest point of a spinning top. The geometry of Pluto's surface is an argument for liquid water inside it. This is an extraordinary claim. It remains unconfirmed. We have not drilled through Pluto's crust. We have not measured the ocean directly. But the evidence from the surface, from the alignment of features, from the behavior of the crust, from the patterns of geological activity, points in one direction. And that direction is deeply unsettling. Because it means that liquid water, the one substance we associate most with the possibility of life, may exist on a world we would write off to be too cold, too far, too small to be worth thinking about. Here is something that should not be possible. Pluto has an atmosphere. Not a thick one, not one you could breathe or even detect with sensitive instruments, but a real atmosphere. Nitrogen, mostly, with traces of methane and carbon monoxide. A thin, hazy envelope clinging to the surface of a world that can barely hold on to it. Pluto's gravity is weak, so weak that if you weighed 70 kilograms on Earth, you would weigh less than 5 kilograms on Pluto. At that gravity, atmospheric molecules can reach escape velocity and drift away into space over geological time. And yet, Pluto still has an atmosphere, which means something must be replenishing it continuously against the constant drain of gravity and solar wind. That something is the surface itself. When Pluto's elliptical orbit carries it slightly closer to the Sun, even the tiny additional warmth is enough to cause frozen nitrogen on the surface to sublime, to transform from solid to gas without passing through a liquid phase. The surface exhales. Nitrogen rises from the plains. The atmosphere thickens slightly. The sky above Pluto, if you were standing there watching, would become marginally less empty. Then Pluto drifts outward again. The temperature drops. The atmosphere begins to fall. Not as rain, not in snow in any familiar sense. Nitrogen snows down onto the surface, a thin, red-tinged precipitation that coats the landscape in frost and waits for the next time Pluto swings close enough to the Sun to begin the cycle again. This process takes hundreds of years. A single Plutonian year lasts 258 Earth years. In the time it takes Pluto to complete one orbit, 24 generations of humans have lived and died. And through all that, the atmosphere breathes, rises and falls, thickens and collapses, carrying material from one part of the planet to another in a slow, grinding weather system that no one had predicted. New Horizons photographed the atmosphere on the way out, looking back towards the Sun. The image showed something beautiful and haunting. Layers of blue haze stacked in bands above the surface, lit from behind by the distant Sun. Blue haze on a world of nitrogen ice and methane frost. A sky with color. A sky that exists at all on a world that should have no sky.
Pluto is not alone. It has 5 known moons, 5 separate worlds orbiting a dwarf planet in the outer solar system. The largest, Charon, is so big relative to Pluto that scientists sometimes call them a double planet system rather than a planet and its moon. Charon is roughly half the diameter of Pluto. If Earth's moon were half the diameter of Earth, it would stretch roughly 6,000 kilometers across. It would dominate the sky. You would be able to see its surface features with your naked eye. That is the scale of the relationship between Pluto and Charon. 2 worlds locked in a gravitational embrace so tight that neither one rotates independently of the other. They have stopped spinning relative to each other entirely. If you stood on the side of Pluto that faces Charon, you would always see Charon in the sky. It would never set, never rise, just hang there, enormous and close, 6 times larger in Pluto's sky than our moon appears in ours. And Charon has its own story to tell. Its north pole is stained a deep red. This region is called Mordor Macula, a name borrowed from Tolkien's Dark Land. The stain comes from something called tholins, complex organic molecules built when ultraviolet radiation from the sun breaks apart methane, and the resulting fragments reassemble themselves into long, complex chains. The methane that makes those tholins doesn't come from Pluto itself. It comes from Pluto. Pluto's thin atmosphere leaks nitrogen and methane into space. Some of that material drifts outward and lands on Charon's north pole, where it freezes, accumulates, and gets processed by sunlight into dark red organic chemistry. Pluto is painting its own moon, one molecule at a time, over billions of years. The 4 smaller moons, Styx, Nix, Kerberos, and Hydra, are stranger still. They do not rotate at a predictable rate. They tumble. Most moons in the solar system are tidally locked to their parent body. Like our moon, they always show one face. But the small moons of Pluto spin chaotically, tumbling end over end, their rotation rates changing unpredictably as they are pulled and tugged by the competing gravitational influences of both Pluto and Charon. If you stood on the side of Pluto that faces Charon, you would never see the sky twice. Pluto and Charon would swing across the sky in constantly changing arcs, sometimes rising in one direction, sometimes in another. The day-night cycle would shift and lurch unpredictably. It would be deeply, profoundly disorienting, even for someone who grew up with sunrises and sunsets and the reliable rhythms of a stable world. In 2006, the International Astronomical Union voted to redefine the word planet, and Pluto did not make the cut. The new definition requires a planet to do 3 things. First, it must orbit the Sun. Second, it must have enough gravity to pull itself into a roughly spherical shape. Third, it must have cleared the neighborhood around its orbit.
Pluto passes the first two. It fails the third. The Kuiper Belt, the vast region of icy debris that stretches from Neptune's orbit outward into deep space, is Pluto's neighborhood, and Pluto has not cleared it, not even close. Pluto is just one object among thousands in the Kuiper Belt, a large one, an interesting one, but not a dominant one. It does not gravitationally dominate its orbital neighborhood the way Jupiter dominates its region of the solar system, sweeping up or flinging aside everything that crosses its path. And so it became a dwarf planet, the largest known member of a new category, one of perhaps hundreds of similar objects scattered through the Kuiper Belt and beyond. Many scientists and most of the public were uncomfortable with the decision. The astronomer who discovered Pluto's largest moon refused to accept it. School children around the world protested, and the scientists who had spent their careers studying Pluto pointed out something important. The definition was based on an object's location and orbital dynamics, not its geology, not its internal structure, not the complexity of its surface. Under that definition, Earth would not qualify as a planet if it orbited at Pluto's distance from the Sun. Earth itself would fail the neighborhood clearing test in the Kuiper Belt. The debate about Pluto's status has never fully resolved. Some researchers still argue for a geophysical definition of planet, one based on what a world is like, not where it happens to orbit. Under that definition, Pluto qualifies easily. It has mountains, it has plains, it has an atmosphere, it has weather, it has moons, it may have an ocean. Whatever you call it, Pluto is not simple. Pluto is not dead, and Pluto deserves more than a footnote.
Let's go deeper. Because the surface of Pluto, strange as it is, may be the least interesting part. Inside Pluto, below the water ice crust and below the hypothetical liquid ocean, lies a rocky core. A core made of silicate rock and metals, similar in composition to the inner planets. That core contains radioactive elements, uranium, thorium, potassium, elements that decay slowly over billions of years, releasing heat as they do. On Earth, this radiogenic heating contributes to the warmth of the planet's interior, to the convection of the mantle, to the movement of tectonic plates. On Pluto, so far from the Sun that solar heat is essentially irrelevant, this internal radioactive warmth may be the only significant heat source the planet has. And according to some models, it may be enough, just barely enough. Enough under the right conditions to keep a layer of water liquid between the rocky core and the icy crust. That ocean would be unlike anything on Earth. It would be cold by any standard we normally apply, perhaps hundreds of degrees below water's normal freezing point, but kept liquid by the pressure of kilometers of ice overhead and the slow warmth radiating from below. There may also be ammonia dissolved in that water. Ammonia acts as a natural antifreeze. It lowers the temperature at which water freezes significantly below zero. An ammonia-water mixture, deep beneath the surface of Pluto under enormous pressure, heated gently by decaying radioactive rock, might be liquid even now. The implications are staggering, because if there is liquid water on Pluto, if there is chemistry occurring at the interface between rock and water, in an environment sealed off from the cold of space, protected from radiation, and supplied with chemical energy from the dissolving rock itself, then we have to ask the question scientists have learned never to assume the answer to. Could something be alive down there? We do not know. We have no way to know with the data we currently have. But consider this. On Earth, we have found life in environments that would have seemed equally absurd a century ago. In volcanic vents at the bottom of the ocean, where temperatures exceed 400 degrees Celsius and no sunlight has ever penetrated. In the hyperacidic water inside active volcanoes. In Antarctic ice sheets, hundreds of meters below the frozen surface. In solid rock, 2 kilometers underground, where the only energy source is the slow chemical reaction between water and stone. Life on Earth has colonized every environment we once thought impossible. If it can do that here, where it evolved under the relatively comfortable conditions of a warm, wet, sunlit world,
What might it do in an ocean that has been liquid for 4 billion years? Undisturbed, protected, patient. Pluto is not the edge. Beyond Pluto lies the Kuiper Belt, a vast flat ring of icy objects extending roughly Neptune's orbit to about 50 times the distance from Earth to the Sun. The Kuiper Belt contains hundreds of thousands of objects larger than 100 kilometers across. Most of them have never been visited by a spacecraft. Most of them have never been seen clearly. They are points of light, or not even that, inferences, mathematical predictions, statistical noise. We know they're there. We know some of them are large. Some may be as large as or larger than Pluto. In 2005, an object named Eris was discovered in the outer solar system. It appeared to be about the same size as Pluto and more massive. The discovery of Eris was what finally forced the IAU to confront the definition of planet. If Pluto was a planet, was Eris? What about the others that would inevitably be found? Beyond the Kuiper Belt lies the scattered disk, a more diffuse population of objects with orbits that were disturbed by Neptune's gravity long ago. And beyond even that lies the Oort cloud, a vast spherical shell of icy objects extending halfway to the nearest star. We have never reached the Oort cloud. We have no spacecraft anywhere near it. It exists in our models, inferred from the orbits of long-period comets that occasionally fall inward toward the Sun. The outer solar system is not empty. It is a vast, cold, dark, and complex territory full of worlds we have not visited, chemistry we do not understand, and processes we have never witnessed. Pluto was the first object in this territory to be seen clearly, to reveal what it was actually like up close. And what Pluto revealed changed the picture completely. If this supposedly dead, frozen dwarf planet has nitrogen glaciers and mountain ranges and a possible subsurface ocean and an atmosphere that breathes, then what are the other objects out there doing? What is happening on Eris, on Makemake, on Sedna, that mysterious elongated object whose orbit takes it thousands of times farther from the Sun than Earth's? We don't know. And that unknown territory, that vast, unexplored outer region of our own solar system, may hold more surprises than anything we have found so far.
New Horizons did not stop at Pluto. After its brief, blazing encounter in 2015, the spacecraft kept moving, outward, away from the Sun, deeper into the Kuiper Belt. In January 2019, New Horizons flew past another Kuiper Belt object, a small, reddish, strangely shaped world now named Arrokoth. It is roughly 35 kilometers long, and it is shaped like a snowman. 2 lobes, each roughly spherical, joined at a narrow neck. Scientists believe Arrokoth formed by the slow, gentle coming together of 2 separate objects that had been orbiting close to each other for millions or billions of years. They drifted toward each other under the influence of their mutual gravity until they touched. Not a violent collision, not an impact, a gentle embrace billions of years ago in the cold outer reaches of the solar system. The surface of Arrokoth is covered in methanol ice and complex organics, tholins again, the same dark red organic chemistry that paints Charon's pole and tints the surfaces of objects across the Kuiper Belt. Arrokoth is old, perhaps as old as the solar system itself. Its surface has barely been touched by the geological processes that reshape worlds closer to the Sun. It is a fossil, a relic of the solar system's earliest chemistry. And what it contains, preserved in that ancient surface, may tell us something about how the building blocks of life were assembled in the early solar system. New Horizons is still moving. It is now more than 8 billion kilometers from Earth. Its power is fading. Its instruments are slowly being shut down. By the early 2030s, it will no longer be able to communicate with us. It will drift on, past the heliopause, the boundary where the sun wind gives way to the interstellar medium, into the true space between stars, where no human-made object has ever gone with instruments designed to look back and measure what it finds. New Horizons will become one of the most distant objects humanity has ever built,
a message in a bottle thrown into an ocean with no far shore. And it will carry with it everything we learned at Pluto. The knowledge that small worlds can be complex, that distance from the sun does not mean death, that ice can build mountains, that darkness can hide oceans, that our solar system is stranger, richer, and more alive than we had any right to expect. There are thousands of exoplanets, worlds around other stars, detected in their masses and orbits by telescopes watching for the flicker of distant suns. Many of those worlds are small and cold, located far from their stars, written off in our mental models as frozen and dead. Before New Horizons, that assumption seemed reasonable. After New Horizons, it seems naive. If Pluto, a world so small that it was stripped of its planetary status, so distant that the sun is just a bright star in its sky, so cold that its atmosphere periodically freezes solid and falls as snow, if that world has geological activity and weather and a possible subsurface ocean and complex organic chemistry spread across its surface and its moons, then how many of those thousands of cold, distant exoplanets are doing the same thing? How many of them have oceans under the ice that we are currently assuming don't exist? How many of them have atmosphere and geology that we are currently treating as impossibilities? The answer, based on what Pluto taught us, is probably more than we think, possibly many more. Our models of planetary habitability were built around the assumption that liquid water requires warmth from a star, that life requires proximity to energy, that cold equals dead. Pluto is the data point that breaks that assumption, or at least bends it, suggests that the zone of possible habitability is not a narrow ring around a star, but something more expansive, something that extends to the very edges of solar systems, something that might even exist in the interstellar space between stars, in rogue planets wandering in permanent darkness. We don't know, but we are asking the question now, which we were not asking before July 2015. And the reason we are asking it is a small, reddish, heart-shaped world at the outer boundary of our solar system. Right now, as you read these words, Pluto is continuing its long, slow orbit. It has been orbiting the Sun for 4.5 billion years. In all that time, it completed roughly 18 full orbits. It does not know we exist. It does not know it was discovered. It does not know it was named. It does not know it was demoted, debated, dismissed, and finally, in 2015, seen clearly for the very first time. It simply moves. Its nitrogen glaciers turn. Its mountains stand. Its atmosphere rises in the relative warmth of perihelion and falls in the cold of aphelion. And beneath its frozen crust, if the models are right, an ocean sits in darkness. It has been sitting there for billions of years. It will continue sitting there long after every civilization that has ever existed on Earth has risen and fallen and been forgotten. We sent one spacecraft past it, one, for less than a day. And in that single day, we learned enough to rewrite our understanding of the outer solar system. Imagine what we would learn if we sent something designed to stay, an orbiter, a lander, something that could drill into that ancient crust and listen for what might be moving in the dark water below. There are missions being proposed, scientists working on the calculations, engineers sketching the designs. A Pluto orbiter would take decades to reach its destination. Anyone who starts building it today will likely be retired or dead before it arrives. But that has never stopped us before. The team that built New Horizons waited 9.5 years for their flyby, 24 hours of data after nearly a decade of travel. They did not consider it a poor return on investment, because what they found was worth every year of waiting, worth every calculation and course correction, worth every anxious night wondering if the spacecraft would survive. Pluto was worth it. And whatever waits at the bottom of that hypothetical ocean, whatever chemistry is occurring in that ancient water, whatever secrets are preserved in the ice of the Kuiper Belt, will be worth it too. We are just beginning, at the very edge of the solar system, on a world that most people have already forgotten. The most interesting questions of our time are still waiting to be asked. Pluto is not an ending.